As an example, a massive MIMO antenna with 128 antennas elements would require 128 simulations. So one of the things that the Wireless InSite MIMO capability has been developed to handle is to deal with this potential for a large increase in simulations. We've included a number of optimizations that help to overcome this. To start with, we use our GPU-accelerated and multi-threaded X3D array model, and then we incorporate two additional key optimizations. The first is something called adjacent path generation that calculates path data in detail for a coarse set of data and then adjusts it to the MIMO antenna positions. And we have an additional MIMO optimization that then quickly finds the precise paths to the elements of the array. The key here is that we keep track of all of the path data. We adjust paths including all of the reflections and diffractions in the scene. And we manage all of this data and capture it for all of the pairs of antennas at the transmitting and receiving elements of the MIMO system. With these optimizations, we're able to do this while minimizing how much additional calculation time is required to perform the simulations. And those optimizations were critical for the massive MIMO simulations that we're going to show in this webinar. So once we calculated the complex channel matrix, we applied two different beamforming techniques to evaluate how beamforming would perform in our urban environment. The first technique is called maximum ratio transmission, or MRT. This sets the beamforming weights for the elements of the array to maximize the sum of all the channel gains to an intended device. On the diagram at the right, the intended device is shown in red, and other neighboring user equipment or devices are shown in blue. And as shown in this beam, there's no attempt made to minimize interference to these other devices. If they happen to be in the beam, then they'll have strong interference as well. The second technique is called zero forcing. In this technique, the beamforming attempts to minimize the interference to all of the users in the cell, placing them within local nulls. So if we look at the bottom of the screen, bottom right, we can see the same case, the same positions of an intended device in red and two neighboring devices in blue. And in this case, the neighboring devices have been placed into a null in the beam so that they don't receive very much interference. For this study, we developed some analytical tools and applied them to the simulation results. And these tools are essentially a preview of future capabilities that are planned in the roadmap for Wireless InSite. So in this diagram we show we had the inputs to the scenario, the antenna array, the urban geometry. We perform Wireless InSite simulations. These generate what's known as a complex channel matrix, and then we performed beamforming post-processing on these to calculate beamforming weights and calculate the beams, the power, and the signal interference plus noise for all of our devices in our scene.